Okay, so this is a kind of short lecture on just the first basic application of derivatives, aside from what we've already talked about in terms of just, kind of talking about slope and shapes of graphs and things like that. The first of what will eventually be many applications of the derivative is to come up with the equation of what are called tangent lines. And, it's a reasonable question at this point in the semester to ask, why the hell do we actually want to calculate this derivative? Why do we really care a whole lot about the slope anyway? So, these are all sort of very reasonable, reasonable things to be wondering about. So, to try to provide a little bit of some basic information about why we might want this, tangent lines, or the equation of a tangent line, is at least a very simple, easy to get to application. And then as we go throughout the semester, we'll see some others that are probably a bit more exciting. But just a basic application first, and this will also just be a nice quick reminder and review of what the derivative represents, in case you're still not totally sure what that actually is. And I understand it takes some time. It's reasonable that it takes some time to get a firm grip on exactly what is this thing. So, okay, so just to sort of recap, where are we? So if we have, of course, any equation, we could, of course, graph that. And I'll just make up just a general function here, just sort of a squiggly sort of a guy. Okay, so that's some function which we've been all semester now calling f of x. So that's the graph of f of x. And okay, what we've been talking about in terms of the derivative, right? So the derivative of f, or the derivative of this function, remember, the derivative, which we denote that way, is just simply the function whose values are the slopes, or whose y values, if you want to say up there, y values are the slopes of the graph of f of x. Okay, so quite simply, when I say, for example, if f prime of, I don't know, let's maybe make up a number over here. Let's say that's maybe 4, x equals 4. So if I say f prime of 4 is 2, I just made all that up, right? But if I say that, okay, what does that actually mean? So the derivative, right? So that's this guy here, the derivative. Now the 4 here refers to x equals 4. In other words, it means I'm talking about what's happening at x equals 4, which on my graph, at least, that would be sort of up here, right? That's above, or that's the point, whatever, I don't know what y value that is, but that point right there, that's talking about what's happening to f, the function, at x equals 4, is namely, it's at that point right there, whatever that y value might be. It's at 4 comma whatever that looks like, maybe 4 comma 1 or something like that. So what is this, right? So what is, if I say f prime of 4 equals 2, what does that actually mean? So that's just saying that this is the derivative, because I have the little mark here, at x equals 4. Again, in parentheses, that's always saying, well, what x value are we talking about? Oh, 4, okay. So this is saying the derivative at x equals 4 is equal to 2. Okay. Well, the derivative is what I've just rewritten here, that I've written many times already, right? The derivative simply tells you about the slope of the graph of f. So in particular, if I say f prime of 4 equals 2, what this is just really saying is that the slope of the graph of f of x at whatever x value I named, which happened to be 4, I just made that up, but 4, is 2. Okay, so that's the, interpretation of what that is, right? So those mean the same thing. So if I say f prime of 17 equals whatever, that means the slope of f of x at x equals 17 is whatever that number is. Okay, so here by saying, I made up 4 here. I just picked a random point here, x equals 4. Say, all right, well, what's happening at the graph? Well, I don't know. That's kind of referring to this region, I guess, right? So I say, all right, well, fine. There's some y value over there. Again, maybe I'll make up a point here and say that that's 1. Maybe y equals 1. Okay, so that point is the point 4 comma 1. Okay, well, that's really, really basic. That just means that when I plug in x equals 4, I get x equals 1, right? So that just means, right, that f of 4 is 1, right? That's the same thing as saying that the graph goes through the point 4 comma 1. Okay, well, that's algebra or pre-algebra. I mean, that's nothing fancy. What the derivative, right, or what role does the derivative play in this is that the derivative, as always, right, the derivative is always going to tell us about the slope of the graph. Okay, and in some sense, it's sort of like a, I don't know, like a formula, I guess, if you want to say that. It's an equation, right? There's going to be x's in it. And so what does it represent? Well, when we compute it, and we've seen how to do the computation a little bit already, when I compute the derivative, and if I plug in an x value, like again, let's say x equals 4, well, you're going to get some number. I don't know what that number is. I just made this up again, and I said, okay, well, what if you get 2? Well, what does that actually mean? Well, that means that it must be that if you looked at the graph of f of x, then the slope at that same x value, 4, must be 2, or again, whatever number you happen to get here. So what that means is that if I kind of looked and tried to sort of squint, you know, we've drawn these little guys in a bunch of times already. It basically means if I try to draw a line that goes through 4 comma 1, make the dot a little fatter so it looks like it goes through there. If it's supposed to have the same slope as the graph, well, then that must be a slope of 2. Because again, the derivative tells you what is the slope of the graph of f of x at any x value. So if for some reason I'm obsessed with what happens at x equals 4, then if I take the derivative and plug in 4, which is like what we would do, you know, algebraically, I just made up this example, but whatever number you'd get, 2 in this case, that means that the slope, right, or if you want to go back to algebra class, m, right, m equals 2 for that line that would sort of, I don't know, we might say sort of touch, it would sort of just sort of be touching the graph right there at 4 comma 1, would have a slope of 2. And in fact, if we had a formula for the derivative, if we knew that, you know, the derivative was, you know, I don't know, 1/2 x, which I guess it could have been in this case, because if I would plug in 4, I would get 2. But I could plug in any x value I wanted. If I wanted to know what's happening at some other x value, I could just plug that in, and that would tell me the slope at that point. So in that sense, again, sorry, I keep making things up. I swear I'll do a real example in a second. But when we actually, you know, if we've done some steps to compute the derivative, it's actually a very powerful thing, because this then could tell you, or does tell you, what is the slope at any x value. If you want to know the slope of this graph over here on the left, at any x value, you just plug it in there, which means, of course, you plug it in there, and then whatever number you get, that's the slope of the graph at that x value. So we could do, you know, what I just sort of made up here, you know, tell a little story like this, then at any x value you wanted. Because how would I figure out these pieces, I guess? Well, if you have an x value, you can always figure out a y value just by plugging it into the function. That tells you the point. And then with our newfound skill of doing the derivative, if we could calculate the derivative and plug in that x value, it would give us the m, the slope. Oh, okay, and if you have a point and you have a slope, then we know that those are 2 ingredients, or the only 2 ingredients we need in order to write down the equation of a line. Is if I know the slope and I know a point on that line, I could figure out the equation of that line. And that's exactly what this topic, I guess, is about, the so-called tangent line. All right, so let me formalize this a little bit for you. So, so for any function f of x at any x value, let's just call it a. So let's say we're going to be, you know, concerned with what's happening at x equals a, where a is just any number. Okay. We define the tangent line to the graph, or to f of x at this point, to be the line that touches the graph at this point and has the same, you could either say slope, or if you want to just sort of be generic, you could say direction. Okay, so the concept of what is a tangent line is actually very simple, and I'm going to draw you a picture. If these words don't make a whole lot of sense, a picture will probably be more reasonable. So if you have any graph at all, again, I'll just sort of make something up here. So that's the graph of f of x, whatever that function is. To talk about the equation of a tangent line, or I should say, just what is the tangent line to begin with? Well, you can pick any x value you want. Let's say I picked that to be the x value that I'm interested in, which I'll just generically call it a. Then what is the tangent line? So the tangent line is, and I'll switch colors here, is quite simply it's just sort of a fancy name for somebody who we've been talking about all along. The tangent line is quite simply, if you went to that point on the graph, okay, so there in blue, and you drew a line that just basically touches the graph right there and has the same direction that the graph has right there, that is what we would call the tangent line. All right, so I'll just draw it in blue here. So it goes through that point right there, and it sort of goes in the same direction as the graph. Okay, so, you know, it's just sort of something that kind of looks like that. Okay, because that goes through that point there, and it has, you know, roughly speaking, to the best of my artistic ability, has the same direction as the graph, the red, does right there at x equals a. Now, if I tried to tell you that, you know, oops, sorry, that was bad, bad for many reasons. If I tried to tell you that that was the tangent line, well, that would be wrong, because yes, that line, that last line I just drew, it does go through that point. But it does not have the same direction as the graph, right? The last line that I just drew there goes uphill, and the graph quite clearly goes downhill there. So that's not what I'm talking about, right? So I'm talking about the line, right, that goes through that point right there, whatever that point might be, and has the same slope or the same direction as the graph, the red. And there is only one such answer, because, of course, we know what the slope of the graph is going to be at that point. That's what we're going to use the derivative for. And we know we're going to figure out what that point is as well. So there's only one right answer to the tangent line. There aren't many. But of course, if I pick a different point, if I pick a different x value, then I get a different tangent line. So for example, if I picked that point over there for some reason, and I called that point, you know, A2. Okay, well, I could say the same story, right? I could say, all right, so go up to the graph. There's some point there on the graph. And what is the tangent line at that point? Well, again, I would just sort of come here and try to draw as best I can a line that looks like it kind of goes through that point and has about the same slope as the graph at that point. Okay, so these would each be examples of tangent lines. Okay, so it is literally the easiest and sort of most basic application of what could the derivative maybe help us do, because these pictures look pretty similar to the pictures that I think we drew when we were kind of exploring what is a derivative. So it's sort of just the most basic and simplest application, I guess. So that's why we'll talk about it first. Okay, so that's conceptually, I guess, what a tangent line is. So certainly drawing one is not a big deal. You take an x value, you go up to the graph and put the appropriate dot there, and then you just try to draw a line that has the same slope as the graph. So, but all right, I think we've moved past just sort of this guessy sort of thing, and we do want to maybe be able to be a little more scientific. Sure, it's nice to draw a picture of that, and I just did that, and I think you all can do that. But of course, I maybe should be able to do a little bit more. In fact, I think I should maybe be able to figure out what's the equation of that line. You know, what is the y equals mx plus b that describes that tangent line? Because I think that would be, you know, a little more scientific. I'd have a precise answer to the question, what is that? Who is that line? Okay. So while I still have this picture up here, let's just do a little bit of thinking. So, all right. So I know if I'm going to write down the equation of a line, I need to know m, which is the slope of the line, and I need to know b, which would be the y-intercept. So, okay, well, if I figure out the slope, you can figure out b as long as you just know one other point. It doesn't actually have to be the y-intercept. So as long as I know a point that's on the line and the slope of the line, that's going to be good enough. So for these tangent lines, like let's just focus on the first one for a minute, if I knew a specific point, in other words, you know, an a comma b or an x comma y, and I knew the slope of this little tangent line that I drew in there, I think I'd be all set, or I think I could figure out then precisely what is the equation. But I think this is hopefully setting up for us to be something that I don't need to do a whole lot of work in order to figure out, because why? What is it that I know? If I want the equation of the line, I'm going to need to know, again, the slope, and I need to know a point. Well, so to derive the equation of the tangent line, we need two things. One, we need the slope of the line, and we need to know a point that's on the line. Okay, but I think we know what the slope is, because if you remember, this is sort of the whole point of talking about derivatives, is that where am I going to come up with the slope of the line? Well, if I compute the derivative, which we know how to do at least in a limited way, and plug in whatever x value you care about, which we'll stick with a since that's what we're using on this slide here. If you plug in x equals a, that gives you the slope of the graph of the red at x equals a. In other words, it gives you exactly the slope of this little line guy that we've been drawing in a million times. Okay, so that's great, right? So the slope of this line, then, I have to compute the derivative, and if I plug in x equals a, that gives me m, right, for my y equals mx plus b. All right? So that's nice. So I'd know what m is, which means my equation would look like y equals some number, because I'd know what m is, x plus b. So then all I'd have to do is run a point through that line, an x comma y. And if I did that, I could solve for b. All right, so I'll show you. Of course, I'll do an example of this in a second. But so the other thing I would need then is a point that's on the line. Okay, so sorry, I've really made this line really fat. But here, let me try to make it a little skinny again. So I'll use the derivative to figure out the slope, but then I need to know a point that's on that line. Well, the only point that I really know for sure is on that line is right there, because it has to go through the point that's in question here. So how do I figure out that point, that x comma y? Well, I know the x value. It's this a, whatever x value we care about. So I know that a, and then what is the y value? Well, that's just asking the question, what's this, right? Or what's the y coordinate, right? Oh, well, f of x, remember, y is the same thing as f of x. So if I plug in a into f of x, that should give me the corresponding y. Okay, so I might just sort of write it this way. What is the point that I know I have? Well, the x value is a, whatever that number is, And how do I get the y value? Just run it through the function. So I might just write it that way, where I'd say, okay, so plug a into f of x, and that gives you the corresponding y. Oh, so that's the point that the line goes through, and you'd have the slope from up here, which if you put that all together, that gives you the equation of the line. Okay? So we have our answers here, right? Or if you want to say these are sort of the steps, I guess, that we might do. Sorry, let me say one more thing here. So then I'd say plug the point and slope into y equals mx plus b to solve for b. Okay, sorry, that got a little cramped in the corner there, so let me come out to a fresh slide here. All right, so an example. So I might ask something like, what's the equation of the line tangent to, and let's use our favorite function because we've done it a bunch of times already. Let's just use the basic parabola, f of x equals x squared. And then let's maybe just do two parts here, so just to give us two examples. Let's say at x equals 2, and then maybe let's do it again at x equals, let's say, I don't know, -1 or something like that. Okay, so you don't have to draw the graph, but just so we have a little picture, I know we all know what this graph looks like, I hope. This is just a basic parabola. Okay, so there's our guy. So let's say that this is the question, right? Tell me or write down the equation of the tangent line to just the parabola, y equals x squared, or f of x equals x squared, at, and then let's do two examples. Let's say at x equals 2, and then let's also say what happens at x equals -1. All right, so x equals 2 is kind of over here. And we actually kind of, well, okay. So we know what point this is, right? This is the point 2, 4. Sorry about that. Right, because this is the equation that I'm graphing here is f of x equals x squared. So when x is 2, y is 4, right? We know that. Okay, so we already know the point, and so all I really need to know is what's the slope, which again, just I'm sort of imagining, well, my tangent line is going to kind of look like that, I guess, or something like that. It's not a very good drawing there, but you know what I mean. It touches the graph right there and has the same slope as the graph right there, so it's sort of like that. All right, so I know the point is 2, 4, right? So the point that the line goes through is 2, 4, which again is just x, the x value that I care about, 2, plugged into the function, which gives you 4. Okay, so 2, 4, that's the point. So the other thing I need to know is what's the slope. So in order to do the slope, I need to compute the derivative. So, so I need to compute the derivative of x squared, right? My f of x for this whole problem is the parabola x squared. Well, I'm going to spare us, a 5-minute problem here because we've done this one already. So if you flip back into your notes, x squared was sort of our classic example that we computed the derivative of the long way with the x plus h and all that stuff. And I'll just remind you that we already did this and that the derivative of x squared is 2x. Okay, so if you didn't know that already, right, and hadn't already done that, you'd have to actually do the derivative right now, which is to say you'd do the f of x plus h minus f of x over h and do that whole thing. But we already did that, so let's save ourselves those steps and just say, well, we already computed that the derivative is 2x. Okay. And remember, what does the derivative tell you? This literally means, right, this guy means that at any x value you care about, the slope of the graph on the right here will be 2 times whatever that x value is. So if you want to know what's happening at, and we want to know what's happening at x equals 2 right now, right? So this whole part is about what's happening at x equals 2. So if I wanted to know the slope, I would use the derivative, and I would say, oh, okay, well, the slope is 2x. Oh, okay, but the x value that I care about right now is x equals 2. So I'll plug 2 in to the derivative, and I'll get, what, 4. Okay, so again, right, another way of saying this is that this is f prime of 2, if you want to say that, right? This is the derivative with 2 plugged in for x. Okay, so the derivative with 2 plugged in for x. Okay, that's 4. Okay, so that's the slope. Oh, so we've got our two pieces now. The slope is 4, and the point is 2 comma 4. So I think armed with that, we can write down the equation of the tangent line. Okay, I didn't leave myself enough space, so let me come down here. So if I want to put these pieces together, I say, all right, so I know what the slope is. The slope is 4. Now remember, I'm going for a y equals mx plus b thing. So I say, all right, well, I already know the slope is 4, so let's fill that in, because it is, right? That's the slope. Okay, so I have y equals 4x plus b, but now I want to know what b is. Well, how do I figure out b? Well, I have this point here, 2 comma 4, which I know means that the line that I'm trying to draw here, or the line that I drew, and the equation of the line that I'm trying to compute here, has to go through that point, 2 comma 4, which means if I plug in x equals 2, I need to get y equals 4 as a answer, because that's the only way to guarantee that it goes through that point. So, so the point here, 2 comma 4, that has to work when I run it through here. So what that's basically just saying is if you plug in x equals 2, you must get y equals 4. And I can do, that's 8, so I think you get negative 4 is b. Oh, okay, so now I'm all done. Now my equation then, so the slope was 4, we knew that already, and we just computed that b is negative 4. So that's the answer. That's the equation of the tangent line. Okay, so so that hopefully makes sense. It pretty much always works this way, so there's not a whole lot of curveballs here. So I was going to ask you, or I will ask you maybe one more point here, just so we have one more example before we move on. What was the other point? I think was x equals negative 1. So part B was to ask the same question, but how about at x equals negative 1? So, okay, so x equals negative 1 is kind of over here, right? So now I'm actually talking about that point. Okay, but similarly, I think I know the coordinates of that point. That's x equals negative 1, because it is. That's the point we care about right now. And what's the y value of this point? Well, remember, this is the graph of y equals x squared, or the graph of f of x equals x squared. So if I wanted to know a y value, I just run the x value through here and see what I get. So if I plug 1 in for x squared, I'm just going to get 1. I'm sorry, if I plug negative 1 in for x, negative 1 squared is just 1. So that's the point, negative 1 comma 1. Okay, and then again, right, just for artistic sake here, what is it that I'm trying to compute now? I'm trying to compute what's the slope of that line. Okay, again, it's the line that goes through that point and just sort of touches the graph, or in other words, sort of has the same slope as the graph at that point. Now, one thing that jumps out at us maybe is that this should have a negative slope, because you can see that, right? The slope is going downhill. So I should get a negative answer for m when I do this. But let's see what I get. So if you want to pause the video and try this just to see how you do, and take 3 minutes, do that, and come back and I'll write out the answer for you. Okay, so I'm going to proceed in the exact same way. I'm going to identify what's the point that I have, and then I'm going to try to figure out what's the slope. Okay, I'm going to do it in the exact same way. So for the point, well, I already have the point. That's what we just did, right? So I know that the point that I'm going to use is -1, 1. Okay, so that's half of what I need. And the other thing I need is what's the slope? Okay, well, same as I did before. In order to figure out the slope, I'm going to use the derivative. And remember, again, since we did this problem already, the derivative of x squared, remember, that's our f of x way up here in the corner. That's the parabola, x squared. The derivative of x squared we did turns out to be 2x. So I already know what the derivative is. And so all I need now is to plug in my x value. Because remember, the derivative tells you the slope at any x value you want. Well, I care right now about x equals -1. So I'm going to plug in x equals -1, which of course should give me -2. And that's the slope. Okay, and just as I said a second ago, right, it looks like this line kind of goes downhill. So it's good that I got a negative number for the slope. Okay, so I have to pull these two pieces together, and I've kind of run out of space here. So if you'll allow me, I'm going to cheat and erase this. But you've already copied this down in your notes. So I'm just going to recycle where I finished that problem and use it to finish this one. So now my goal is to figure out what is the y equals mx plus b that is the equation of this line. Well, I have all my pieces here. I just have to organize my thoughts now. So I have the slope is -2. So let's fill that in. So I know that it's y equals -2x plus b. Okay, right, and once you figure out the slope doesn't change, right? The slope of this line that I drew in here, this guy, that's always -2. Because the point is that it's a line, which means it's straight. So if the slope is -2 right there, which is what we computed, well, then it's always -2. Okay, so let's fill that in. So there, so it's y equals -2x plus b. All right, and then I need to know b. Well, and again, the fastest way I know to figure out b is to say, well, but we know a point. We know that when I plug in x equals 1, when I plug in x equals -1, I better get 1 for y, because that's what it means to say that the point is on the line, or that the line goes through that point. So if I plug in x equals -1, I better get y equals 1. Okay, so I can use this now to solve for b. This looks like 2 on the right here. And so when I subtract 2 over there, I get -1 for b. So I put that together with my first fill in, and I think that's my answer. Okay, so like I said, that's a pretty simple application of the derivative. I know probably it begs the question, why the hell do you want to know the equation of the tangent line? And that's a valid question at this point. But that's sort of the most immediate thing, that at least there's well, what do I do with this? Now that we computed the derivative, what might I use it for? And while this is probably a bit of a silly example or silly application, computing the actual slope at a given point is actually quite helpful in terms of what it tells you. It tells you the rate at which it's changing at that point. So this is a nice way of sort of just conceptualizing that and at least doing a basic application. We'll have much fancier, and I promise much more useful and practical applications of derivatives coming at us later in the semester. So, okay, so that's the end of tangent lines, equations of tangent lines. They all work this way. So the only thing that will change is the only step in this entire process that was actually calculus, which was the derivative, right? That was really the only thing that wasn't just algebra. And so, of course, this step, right, computing what is the derivative. Oh, okay. Well, that's what this whole course is about. So, so we do want to pause, I think, and get a little bit better at doing that, maybe before we go ahead and race ahead and do lots of more complicated derivatives. So that's what the next video will be about, is how to maybe be faster at doing derivatives.